Okay, welcome to lecture. Sorry about that. Uh, I signed on and I was the only one here, so I figured that's probably not good. For some reason the wrong one was in there with the right date. So hopefully you saw the announcement. I corrected it. Sorry about that. But it's good. I caught it before I started lecturing and realized I was lecturing to myself. So I guess that's kind of a good thing, I suppose. Okay, we are going to be continuing on here. We're going to finish up chapter 2. We're going to roll into some chapter 3 here. Maybe we just want a longer holiday weekend, I think, maybe. Okay. All right. So last time we were really kind of finished up talking about electron configuration and writing electron configuration. And so remember, if you kind of do that zigzag sort of thing there, it will basically walk you through the correct order to write electron configuration. Remembering that basically S's could hold a maximum of 2 electrons. The P subshell could hold 6. The D subshell could hold 10 electrons, and the F subshell can hold 14 electrons. So you just want to follow that. There are a couple of sort of exceptions, and I think we might have went over, but just to make sure before we kind of finish this up here. Where can I write it? Yeah, I'll write it on top here and then kind of erase it, I think. So a couple of exceptions to the kind of the normal electron configuration order that we would. And there's a lot of exceptions, and 2 really notable exceptions that you should be aware of that does come up a lot is with chromium and copper. So for example, chromium is 24, chromium is number 24 on the periodic table, copper is 29 on the periodic table. And they both have a very similar sort of exception to how you normally would think of the electron configuration. So if we did this again, we would get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. And again, if you sort of follow that zigzag thing that we sort of developed there when we were talking about last week, this is sort of what you would get when you did it for chromium. Now, the exception is actually here. There's actually 1 more electron in the D and 1 less electron in the S orbital. And the correct sort of configuration for chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. It's just been found experimentally to be sort of more stable in that fashion. We also talked about last time that, if you don't want to write the whole thing, you could kind of do the noble gas configuration, which in this case would be argon in parentheses, always a noble gas that goes in that parentheses, or brackets, I guess is a better way of putting that. Then it would be 4s1, 3d5. And again, this would be for chromium. Copper, which is 29, basically has the same sort of exception. It has an extra electron up in the d orbital, 1 less electron in the s. So copper's correct configuration would be argon 4s1, 3d10. So if you kind of think about it, it's a little bit more stable. We have an electron in each of the d's. We have everybody paired off there in the d's with copper. And these are just some that have been found sort of experimentally to be more stable in that configuration. So those are the accepted ones for chromium and copper. Those are the 2 for our class that you should be aware of in terms of electron configuration, and sort of an exception to the normal electron configuration would be those 2 that you should know. In reality, if you look on the periodic table, right around where chromium and copper are, and you go kind of below them on the periodic table, what you will see is a lot more exceptions. Things like silver, for example, is also sort of an exception to the normal filling order. There's things like PD there that has, I think, no electrons in the S. They've all went up to the d orbitals and stuff like that. So there's a number more of exceptions in the transition metal region. But for our class, chromium and copper are the 2 that you do need to know. Now, I think the last thing we're going to kind of talk about here with electron configuration was the idea of what happens with ions, and I don't think we got to that, so I just want to make sure we do. Ions and electron configuration. So remember that when something does gain or lose electrons, it becomes an ion, and a cation, which is a positively charged ion, is from a result of a loss of electrons, or an anion, which is a negatively charged ion, is a result of gaining electrons. So when you do have things that lose or gain electrons, you do have to take that into account to your electron configuration. So for example, if we had magnesium that gained a +2 charge, what that means is +2 means that it actually lost 2 electrons. So normal magnesium with no charge would have 12 electrons, which would be 1s2, 2s2, 2p6, 3s2. When it loses its electrons, it's going to be these two here that are going to be lost. And those are what are referred to as valence electrons, which is on this slide I'm writing all over. And that means that magnesium with a +2 charge would actually only have 10 electrons, which means the electron configuration for it should be 1s2, 2s2, 2p6. If you take something that gained electrons, say something like nitrogen that has a -3 charge, nitrogen with no charge has 7 electrons. With a -3, it means they actually gain 3 electrons. So this guy here as well would end up with 10 electrons. And nitrogen or nitride ion with a -3 charge there would have an electron configuration 1s2, 2s2, 2p6. Now, you may also say that looks very much like neon's configuration, and it is. Both of these guys have now the same electron configuration as neon, and things with the same electron configuration. So if you take something that is neon, for example, nitride, which has a -3 charge, and magnesium with a +2 charge, they are all three what are referred to as being isoelectronic with each other. Isoelectronic means everybody there has the same electron configuration. And as we'll talk about here in the next chapter, that is really the goal of everybody. The goal of everybody in bonding is to get to the same electron configuration as our noble gases. Again, our noble gases are really stable. It's a very stable situation. And that's why everybody wants to get to the same electron configuration as our noble gases. So our representative elements, and when we're talking about that, members of groups 1 through 8, metals there will typically lose electrons, and they will back up to the same electron configuration as the noble gas that comes right before them. And nonmetals will typically gain electrons and go forward on the periodic table to the noble gas that comes right after them. And again, that, as we'll talk about in the next chapter, really the whole point of bonding is to get to that noble gas configuration, and as again a super stable type configuration. Now, transition metals actually work a little bit different, and we're not going to get into too much in terms of transition metals, but just to maybe find a spot where I could scribble here. Let's go. There it is. We'll go here. So for example, if we look at transition metals, something like iron, and iron has 26 electrons, which means if we write the electron configuration, it would be argon 4s2 and 3d6. Okay. And when the electrons go in, as we can see here, they do go into the 4s orbital first, and then they go into the 3d. So, you know, the electrons kind of pile into here, and then the electrons go in here really one at a time and come back. And so that would be sort of the end part of the configuration for something like iron, which is a transition metal. Now, what happens with our transition metals, because they have those d electrons, there's actually a switch in energy that occurs. So although as the electrons are going in to the atom, the 4s orbital is lower in energy, there's actually a switch that happens once you start putting electrons in the d orbitals. And what ends up happening is the s electrons actually become higher in energy, when that switch occurs, than the d electrons. And that affects what electrons will actually be lost when a transition metal actually loses electrons. And when we lose electrons, we always lose the highest energy electrons. And for transition metals and transition metals only, they will always lose the s electrons first. So they always lose those s electrons first. So for example, if iron ended up with a +2 charge here, it would have 24 electrons. And what's going to happen is they will lose these 2 electrons right here first. So they will pretty much take away those, and it will end up with a configuration of argon 3d6. Now, if iron went to, say, +3, it would have 23 electrons. So the same thing would happen. It would lose those s electrons first because they're the highest. And now the only other option is to go into the d electrons and lose an electron there. And it will end up with argon 3d5. So transition metals are a little bit different than everybody else in groups 1 through 8. And again, those transition metals are between groups 2 and 3. When they do lose electrons, they will always lose the s's first and then go into the d's. And that's why sometimes people will consider that transition metals have 2 valence electrons, which are those s's, and some will consider that they could have upwards of like 12 because they have the d electrons as well. So this is something that only really sort of happens with transition metals. And as we start filling those d's, we do get that sort of switch in energy that occurs. But when the electrons go in the atom, they go to the s first and then the d, then they switch. And when they start to lose electrons, it's the s's that always comes first. Question on electron configuration with things with charges. Okay. And for our class, for lecture, and I don't even think for lab, you have to worry too much about transition metals, or anything like that. So if there is anything with a charge, it probably will be somebody from group 1 through 8, but just so you know what happens with transition metals. Okay, now that I scribbled all over the other page, let's talk about those valence electrons there. What I'll do is just get rid of all that, I think. There we go. Now we can actually see it. So let's talk about valence electrons. So valence electrons are the highest energy electrons in an atom. And you could basically figure them out by writing the electron configuration, which is one way that you could do that. And so, for example, here, if we take nitrogen and we write the electron configuration there for nitrogen, what we do see is 1s2, 2s2, 2p3. Remember that these first numbers are the energy levels. So what this really tells us is on the first energy level, there's 2 electrons. Both of these guys have the same number for the energy level, which is 2. And the grand total of electrons on the second energy level is 2 there and 3 there, for a grand total of 5 valence electrons in that second energy level. They don't have to be in the same orbitals as you see, but they're both on the second energy level, and that makes it its valence electrons. So that's one way that you could pretty much figure out the valence electrons, is to write the electron configuration, those last electrons in the highest energy level, which if you're doing somebody in groups 1 through 8 will be pretty much your last guys in the configuration, will be your total number of valence electrons. Who's got time to write all those electron configuration? You don't, you're busy people. So the much easier way to figure out the number of valence electrons is actually just to look at the periodic table. And there's a very simple way to figure it out. The number of valence electrons will equal the group number. So pretty simple. Everybody in group 1 has 1 valence electron. Everybody in group 2 has 2. Everybody in group 3, 4, 5, 6, 7, and 8. That's why if you look on the periodic table at nitrogen, you will find nitrogen in group number 5. And it has, as we can see here, 5 valence electrons. If you look at sodium, which is group number 1, and if you write the electron configuration for sodium, 1s2, 2s2, 2p6, 3s1, these are all lower in energy. Number 3 here is the highest in energy. This would be its 1 valence electron, and the easier way is sodium's hanging out right there in group 1, so it should have 1 valence electron. So you can write the electron configuration, see which ones are the highest numbers in terms of the energy levels, and you can figure out the valence electrons that way. Or my recommendation would be to just look at the group number, and it will equal the group number. Question on that. Valence electrons are really important, as we'll talk about for sure in the next chapter, because they are the outermost electrons. They're the one highest in energy. They are the ones that basically are involved in bonding. They're also the ones on the outside of the atoms. So when two atoms come together, they're like the first ones to say hello to each other. So they obviously are important sort of electrons. So here's just some examples. Fluorine, which is group 7 on the periodic table, has 7 valence electrons. Chlorine, which is 7 as well, has 7 valence electrons. Carbon, which is group number 4 on the periodic table, would have 4 valence electrons. And again, it's those guys that are in the last energy levels when you write it on the periodic table. So for example, again, carbon would be 1s2, 2s2, 2p2. And again, these are both on the second energy level. 2 electrons in that guy, 2 electrons in that guy. Gives you the 4 electrons for carbon when you look at his electron configuration. So that's essentially where it comes from. Any questions on valence electrons? Okay, so we're going to talk a little bit about some trends on the periodic table and some important trends. So as we go down a group, and remember a group on the periodic table is up and down as we go there. They do tend to lose their electrons more easily. And so, for example, in order of losing electrons, cesium is easier than obviously lithium. And that's because as you go down on a group, one thing that happens is we do have a larger positive charge. And because we have more protons, we also have more electrons, which means those electrons got to be further away from the nucleus. And because they're further away from the nucleus, they're not going to be held as tightly. And when we look at sort of the periodic table in terms of most reactive metals and nonmetals, the most reactive metal that we typically find is bottom left there of the periodic table. The most reactive nonmetal that we find is usually upper right of the periodic table. And the reason for a lot of that is what we're going to talk about now is some of these sort of periodic trends that help us understand, why that is. So let's take a look at one important sort of trend, and this is what is known as ionization energy. And ionization energy is the energy that's required to remove an electron from an atom in the gas phase. So this is the amount of energy that you need to put in there to basically pry an electron off. And when we pry an electron off, it becomes positively charged or a cation. So we oftentimes think about ionization energy in the formation of a cation. And in terms of the periodic table, what we see is metals have low ionization energy, and that's because metals typically make a positive charge and make cations, so they have low energy, doesn't take a lot of energy to remove electrons. Nonmetals, on the other hand, have usually very high ionization energy because they typically do not lose electrons. They actually typically gain electrons. So when we look at the periodic table in terms of the trend, up and to the right on the periodic table, the ionization energy increases, and left and down on the periodic table, the ionization energy decreases. And again, remember that up and to the right on the periodic table is where we see nonmetals. Left and down is our metals on the periodic table. So again, that sort of makes sense. And this also makes sense with another trend, which is atomic size. As we go to the right and up on the periodic table, the size of the atom gets smaller. As we go left and down on the periodic table, the size of the atom gets larger. And that's because as we go to the right, we're getting a greater positive charge and not as many electrons. So that greater positive charge is going to bring all those electrons in, and the overall size of the atom will be relatively small, as opposed to the left-hand side where the positive charge is not that strong, not as many electrons, and they could kind of spread out a little bit. The reason why these guys, even though they have a greater positive charge, is still larger because with that greater positive charge comes more electrons. More electrons need more space right around the atom. They're going to be able to kind of spread out a lot bigger. So that trend, ionization energy is important, atomic size, and let's just add one more sort of trend to that, which is what is known as electronegativity. And we'll talk more about this as well in the next chapter. Electronegativity is the ability of an atom to attract electrons towards itself. So on the periodic table, it increases as you go this way, with fluorine being the most electronegative element you could have. And it decreases as you go down. So this trend, along with ionization energy, along with atomic size, all helps us understand what we actually do see in terms of elements. And that is, when we see metals, they typically are the ones that will give away their electrons. When we see nonmetals, they are typically the ones that will say thanks and pick up those electrons. So if we sort of look at this little kind of periodic table here, atomic size decreases to the right, ionization energy increases as you go to the right and decreases down. Electronegativity increases this way and decreases coming down. And all this means, if we go again, right-hand side, upper right of our periodic table, we have elements that are very small, which means they're going to hold on to their electrons really tight because the electrons are closer to the nucleus. They also have very high ionization energy, which means it takes a lot of energy to remove an electron. And they would rather not remove an electron. They have very high electronegativity, which means instead of removing electrons, they actually want to bring electrons towards them. And that's why what we see with nonmetals is they typically will form our anions and become negatively charged and gain electrons. And that's opposite if we come kind of this way on the periodic table, left and down. We have something that is much larger in terms of size, which means the outer electrons are further away from the nucleus, not being held as tightly. They also have very low ionization energy, which means you don't have to put a lot of energy in there to make them lose electrons. And they have very low electronegativity, which means they're not really looking to gain electrons. So all those trends make them want to basically give away their electrons. And that's why when we think about metals, they are typically the ones that make cations, which are positively charged, from losing electrons. Any question on sort of those trends there? And while we're talking about anions and cations, a cation is usually smaller than its neutral counterpart. So when something like sodium, for example, loses an electron, its electron cloud gets smaller, which means the size of the ion, the positive ion, is going to be smaller than the neutral guy that it started with. And the opposite is true when we talk about anions, the negatively charged ions. They will typically be larger than the neutral guy they came from. So say something like oxygen, when it gains a couple of electrons, it adds to its electron cloud. The overall size of the negatively charged ion is larger than the neutral ion. Any questions on any of those trends there? Okay, so that wraps up chapter 2. We're going to roll into chapter 3 here. Give me 1 second to get it set up here. Okay, let's go with that one. Do that. Okay, so this is chapter 3. We're going to talk about a variety of stuff here, including naming, how to name everything. We're going to talk about bonding, and hopefully everything looks okay. Yes, the right size and not super small or anything like that. Again, on my side, it kind of always looks the same, so I just want to make sure. All right. So we're going to talk about chemical bonding in this chapter. We're also going to really talk about nomenclature, which is naming. So we're going to really start with the naming part of it. So let's get into some of that there. So nomenclature really is just a fancy way of basically naming things. And there are certain things that have common names that we go by those common names. And here's a few of them on this page. And really, I would say probably the first three here are the ones everybody uses the common name for. H2O, it is not a trick question. That is water. It's not dihydrogen monoxide or anything like that, because nobody wants a refreshing glass of dihydrogen monoxide, right? So if you see it, not a trick question, just put water and go on with your life and all that good stuff. NH3 is ammonia. So that is also a name that you should use. CH4 is the simplest organic molecule you could have, and that is methane. And that name you will know a little bit later on when we get to the organic chapters. But again, you should call it that. I'll be honest with you, most people still call this sodium chloride. Not too many people call it salt, but most people just say sodium chloride. This is also sugar or sucrose. But for us, these three here definitely go by the common name, which again, water for H2O, ammonia for NH3, and methane, which is CH4. And again, we will see something that looks very much like NH3, but it does have a different name. So when we're talking about sort of compounds, and naming compounds, there's really two types of compounds that we're going to talk about. And one is a compound that contains a metal and a nonmetal. And when we do have a metal and a nonmetal, or whenever you have pretty much a metal and nonmetal that comes together, what it forms is really an ionic compound. So this is always what it forms, which is known as an ionic compound. And as we'll talk about when we get to the bonding, what essentially happens in an ionic compound is the metal will give away the electron, and the electron will transfer to the nonmetal. The nonmetal will pick up the electron. And what you end up having is what we've been talking about. Our metal will form a cation, which is positively charged. Our nonmetal will form an anion, which is negatively charged. And what actually holds that compound together, there's absolutely no sharing of electrons here. It's what is known as that electrostatic attraction. That is the fancy word for opposites attract. So it is simply that positive charge and that negative charge that is attracted to each other. And that is what holds an ionic compound together. And you don't even have to think about it hard or anything like that. If you see something that's a metal and a nonmetal, it's a pretty safe bet that's an ionic compound. You know, you don't have to worry about it being something else. And probably 99.9% of the time, it's definitely going to be a metal and a nonmetal. Now, the difference here when we get two nonmetals together, this type of compound is what's sometimes referred to as a molecular compound, or it's sometimes referred to as a covalent compound. And when we get two nonmetals together, the difference though here is there actually is sharing of electrons. So it is the sharing of electrons when those two nonmetals come together that actually will hold that together. And as we'll talk about later in this chapter, the sharing can be equal or unequal sharing of those electrons. But there is some type of sharing of electrons that's happening in a nonmetal when they come together. And that's, again, an important distinction between those two types of compounds. One, metal and nonmetal, no sharing of electrons, transfer of electrons, held together by positive, negative attraction. In two nonmetals, there's absolutely sharing of electrons, and that's basically what holds that unit together. So before we go too far, just to make sure, I think I talked about it, but I just want to make sure. When we talk about the periodic table, and we talk about things that do make charges, So just to make sure I did talk about it with you guys. There are certain things on the periodic table that have sort of fixed charges when they do make charges. And also a reminder that if you take something off the periodic table, like say copper by itself or iron metal by itself, those things really don't have charges. They don't get charges until they basically start to bond with something that's like a non-metal and stuff like that. But everybody in group one, no matter what the situation is, will always form a +1 charge. Everybody in group two will form a +2 charge. Everybody over here in group three, and again, pretty much who we're talking about is aluminum, will always form a +3 charge. Group four, there's really no good pattern that happens there. And again, it's because you have that staircase that kind of comes down through here. And in group five, the non-metal will be -3. Group six, the non-metals will become -2. And group seven, the non-metals will become -1. Non-metals above the staircase and to the right. So things like nitrogen, oxygen, you know, those guys, sulfur is what we're talking about there. Now, in the transition metal region, which is here between group 2 and 3, they typically will have a variety of charges that they can do. And that's going to be important in terms of the naming we're going to be talking about here. But there are 3 exceptions in the transition metal region that does have a fixed charge. And that is zinc and cadmium, which is right about here. Zinc and cadmium will always make a +2 charge no matter what the situation is. And if you hang a left at cadmium, you'll come to silver, and silver will always make a +1 charge. So that kind of backwards L, those 3 little exceptions there in the transition metal region, they will have sort of a fixed charge. Pretty much everybody else in the transition metal region and the metals down here below the staircase, these are also metals and not transition metals. So everybody else pretty much around here and in here, they will also have variety of charges. So they will not have a fixed charge. It depends on what they are bound to as to what their charge will be. So that's an important thing to sort of keep in mind as we talk about, obviously, the naming part of it here. So let's talk about naming, and let's talk about type 1 and type 2. So when we talk about type 1 and type 2 compounds, these are when we have metals and nonmetals together. So this is going to be ionic compounds. And let's just talk about the actual ions themselves if you just had them by themselves with nothing else attached. So if you just had, come back here. If we just had a cation, say like H+, we would just use the whole name of it. So that would be known as the hydrogen ion. If we had Na+, that would be known as the sodium ion. And you can see here with our positive guys, we pretty much just use the whole element name, and it's usually a metal. So if we had Ca2+, this would be the calcium ion. And if we had some anions, which is our negatively charged ions, we had something like O2-. O is oxygen. And when we have something that is negatively charged, what we do is we drop the last part of the name and we put IDE there. So oxygen becomes the oxide ion, IDE. Br-, bromine becomes the bromide, IDE ion. Hydrogen is a weird one. Hydrogen can be positive in certain cases. It actually could be negative in other cases as well. And it would be named the same way. It becomes the hydride, IDE ion. So if you have just a positive ion or cation by itself, and you're asked what is the name of the cation, you basically just use the whole element name and you put ion at the end. If you have a negatively charged ion, you basically drop the last part of the name and you replace it with IDE. That's why there actually is a difference if you say, I have bromine or I have the bromide ion. The bromide ion is bromine with a -1 charge. Bromine by itself is actually Br2. So there actually is a difference, when you kind of say something. And if you're meaning this guy, which probably most of the time you are, that's why I should have the IDE here. Again, if you just say bromine, it means something without a charge, just the element by itself. So, important to understand the two basic things, and that's going to really help us understand how to name these ionic compounds. Any questions on that there? Okay. All right. Stop going backwards here. I'm trying to go forward. There we go. All right. So when we have an ionic compound, there's a couple of things that's important in terms of the way that you should write these things. It is always the cation first, followed by the anion. So when you write the formula, or you name it, it is always positive guy first, then negative. So it's always positive ion and negative ion. Also, when we write the formula for an ionic compound, it should always equal 0 in terms of the charge. So what do I sort of mean by that? If you look at, say, the periodic table, sodium is in group 1, which means sodium has a +1 charge. If you look at chlorine and chloride on the periodic table, it is group number 7, which means it has a -1 charge. When I put these guys together, that is +1 and -1. That's a grand total of 0 when I add that together. That means it has no charge. And the correct formula would be NaCl. Positive guy first, negative guy second. Now, although when we write the formula for something like sodium chloride, it has no charge written in the actual chemical formula, but it is actually made up of 2 ions. It is made up of this cation and is made up of this anion. But when we do put it together in a ionic compound formula, should always equal 0. And that means sometimes you need more than one of something. So for example, if I took my calcium and hooked it up with my chloride, when I put these together, if I just put it together one of each of these, that would be +2 and -1, which means I would have a +1 charge left over. And to balance it out, I need not one of these guys, but I actually need 2 of these guys. -1 and -1 give me a -2, which balances out the charge on the calcium of +2. And the correct formula here would be CaCl2. Also, the formula here has no charge. Positive guy first, negative guy second. But what this implies is I have 1 calcium that has a +2 charge. I have 2 chlorides that have a -1 charge each. And again, everything is balanced in that sense. Now, sometimes people learn as we will talk about, I'm just going to do the switcheroo type of move. And, you could do that, bring the numbers down and across, and it works, about 95% of the time, 93% of the time. It doesn't work 100% of the time. So it's best to sort of think about it in terms of balancing out the charge to get to 0. But, if you want, you could do that flipperooski there. Again, will not 100% of the time work. 90-ish, 93% of the time. It's not bad, I suppose. But you will get some wrong formulas if you just sort of blindly flop the numbers down and stuff like that. Or flop the numbers up going the other way as well, which is a common thing people do as well. They'll go, I'm going to go this way and this way with the numbers. And again, most of the time it'll work, but there's a lot of times where that will not really work for you. So what really is the difference between a type 1 compound and a type 2 compound? A type 1 compound is a metal and a nonmetal. And whenever you take a metal and a nonmetal together, the really important one to look at is always the metal. So it's always the metal that's really important. And in a type 1 compound, the metal has a fixed charge. So if you remember what we just talked about, the metals that have fixed charges are members of group 1, group 2 on the periodic table, group 3 on the periodic table, silver, zinc, and cadmium. So if your metal in a compound contains one of those guys, a group 1, a group 2, a group 3, zinc, cadmium, or silver, it is a type 1 compound. And the nice thing about type 1 compound, as we will see, is to name a type 1 compound, you pretty much use the whole name of the metal. And then the non-metal, you drop the last part of the name and you put the IDE on it. So type 1, whole name of the metal. Non-metal gets the IDE at the last part of it. And that is all you have to worry about in terms of naming it. Type 2 compounds are compounds where, again, the metal is the important part. The metal is going to be a transition metal. Are just to the right of it, below the staircase. So if you're wondering what I'm talking about there, if you look on your periodic table that you hopefully have one near, that is things like tin, that is things like lead, that is things like bismuth. Those are metals below that staircase, and the antimony in that case. You know, they're technically not transition metals, but they are named the same way. And what all these guys really share in common is they have a variable charge. And as you can see here, in certain cases, for example, chromium could be +2 or +3. Copper could be +1 or +2. And it does matter what they are bound to as to what the charge is. And you do have to take that into account. And as we will see here, but I'll just put it up here, we pretty much name it the same way. We're going to do a whole name of the metal. We're also going to still do the non-metal with the IDE at the end. So you may be wondering, this sounds very similar to the other way. The additional thing that we put between those two things are Roman numerals. So we put a Roman numeral between the name of the metal and the name of the non-metal. And what the Roman numeral indicates is the positive charge on the metal. So if you took one of the metals out, what the positive charge would be on it, and that's what the Roman numeral will stand for. Any questions on that so far? Okay. So let's take a look and see what we got going here. So here is a table, again, of just the ions by itself. On the left there, those are all positive ions. And you can see that they all have the whole name of the element used. And on the right-hand side, those are all negatively charged ions. And you can see that the last part of the name basically has been replaced with IDE, which is what you do for your negative guys. So as I just mentioned there, we're going to go cation first. We're going to use the whole name of the element for the cation, and we're going to put the IDE at the end of it there for our non-metal. So again here, if we took our NaCl and we were given that, this is a metal, this is a non-metal. Again, the sodium is the important part of it. Sodium is group 1, which means we know it always has the same charge. So that tells us that this is a type 1 compound. And that simply means that we just go whole name of the metal, which is sodium. The Cl is our non-metal, so it gets the IDE at the end of it. So chlorine becomes chloride. We do our guy that we had, say, before, our CaBr2. Same thing here. If we look at this guy, this is calcium. If you look on the periodic table, calcium is group number 2. Automatically should tell you no matter what the situation is, calcium will always have a +2 charge. That is a fixed charge for the metal. That should scream to you type 1. And that should also tell you that we just need to use the whole name of the metal. The Br, which is bromine, is the nonmetal, and it gets the BRM bromide IDE. Now, the thing that people love to do is, what about the 2? I know I should use a die somewhere in this name because, hey, there's 2. That makes sense. And you shouldn't, because you're just going to get one of those, maybe a whole bunch of those, a lot of X's happening and stuff like that. The extra 2 there is because of what we were just talking about to balance out the charge. So again, calcium being group 2 is +2. Bromide is group 7 is -1. So again, when we put this together, we need not 1 Br minus, but we do need 2 to balance it out. But what that means when you name a type 1 compound, it has absolutely no effect on the second name. So even if you had a 40 there next to the Br, which you probably won't, but even if you had a 40 there, you would still just call it bromide at the end. So always people want to put that extra die and those prefixes. You should not use those in this case. We will talk about when you should use those prefixes, but this is definitely not the case. So even though there's more than one of that second guy, it has absolutely no effect on the name. Any questions on that? And as I talked about in formulas, we do put it together with no charge, but it does represent something that does have a charge. So as I talked about with the sodium chloride, although when we put it together, the NaCl has no charge, it does represent 2 things that have a charge. Same thing here when we look at Ki, if we wanted to name it and figure out how we got that name. K is a metal. It is group number 1, which means really it is K plus in that situation. I is a nonmetal, which is group number 7, and it is a -1 in that situation. So again, whole name of the first guy, which is potassium. The iodine becomes iodide, IDE at the end of it. And the reason the formula is Ki, because this is +1, this is -1. So when we put it together, we just need one of each of them, and that gives us a Ki. Again, the formula, no charge written. When you put the metal and nonmetal together, the only time something should have a charge is if you write an ion. So if you were asked, what is the cation in that guy, and you want to write the formula for the cation, that's when you would write K+. If you were asked what is the formula for the anion, you would write Cl, actually I- in this case. And if you wanted the formula for the compound, you would write it just like this, no charges when you put them together. So again, that's really important not to include the charges when you actually put the metal and non-metal together in the chemical compound or the formula for it. Any questions on that there? All right, so I think we got some examples here. So why don't you take a couple of moments here and come up with the correct names. Hopefully we didn't do too many of these. And while you're at it, I'm also going to give you some names. Why don't you write the right formulas for this? So why don't you name those 3 guys there, and then let me make some stuff up here. Let's go with magnesium. We'll go with magnesium sulfide. Write the correct formula. Let's do aluminum oxide. Write the correct formula. And why not? Let's do sodium nitride. All right, so take a couple of minutes. Guys on the left, the correct name. One's on the right, correct formula. So see what you come up with. And again, if you don't have a periodic table out, you got one near, you might want to go grab one. It will be probably very helpful in this chapter for sure. Okay, so I see some answers coming in there in the chat. Some's looking good. So let's take a look and see how we did or how we're doing. So we'll start with the first one. Again, you should hopefully be able to recognize that's potassium, that's chlorine. So again, this is a metal and a nonmetal together. So the important part here is always the metal. So if you go to the periodic table, you'll see that potassium is group number 1, which means it has a fixed charge. Also tells us that's type 1, which automatically means we go potassium, the whole name, and chlorine becomes chloride. And again, this is basically made up of a cation that's K+, and this guy here is Cl-. And that's why we just need one of each of those, +1, -1, to give us our KCl. Looking at our second one here, that is Ca, which is calcium, which is a metal, Br, which is our nonmetal, and I think this might have been one that we named earlier. So calcium is group 2, has a +2 charge no matter what the situation is. Br is -1 because it's group 7, and that is why we need 2 of them here to balance it out. 2 minuses and +2 gives us no charge. So same thing here, whole name, which would be calcium. Bromine becomes our bromide like we saw there. Our last one here, which is Ba, which is a metal. Remember, hydrogen is actually a nonmetal. So this is a metal and a nonmetal together. Barium also group 2, which means it's barium with a +2 charge. Hydrogen, when it comes second after a metal, is negative. So this is actually our H with a negative here. Also why we need 2 of them to balance out the charge. But because barium is group 2, we will just use the whole name of barium, and hydrogen will become hydride in this case, IDE. Again, the 2 here has no effect on the name. The 2 here, as we talked about earlier, no effect on the name either. So again, because it's a metal and nonmetal, IDE on the last one, regardless of how many there are, has no effect on it, just like it would have no effect on the first name either. So if I had like 2 potassiums, it would still just be potassium. So you should not use any prefixes in this type of naming. Any questions on the naming part of it there? So let's take a look then at actually doing the formulas. So when you're doing the formulas, same idea. You just kind of work your way backwards. So this is magnesium, which is a metal. Sulfide, which is sulfur, is a nonmetal. So we know this is an ionic compound. We also know that magnesium is group number 2, which means it has a +2 charge. Sulfur, which is group number 6, has a -2 charge. And when we put those together, +2 and -2 will equal 0, which means we actually just need one of each to put it together. This is magnesium with a +2 charge. That's sulfide with a -2 charge. Again, equals 0. This would be a case where you would get the wrong formula if you did the switcheroo and you wrote Mg2S2. Technically speaking, that is wrong. And is wrong because it should be this. Ionic compounds are always the simplest combination that comes together. So that's why it would technically be wrong. Aluminum here is group 3 and a metal. Oxide is oxygen, which is group 6 and a nonmetal. Aluminum is group 3, as I just mentioned, which is +3. Oxygen is group 6, which is going to be -2. So now when we put this together, we want to look for the common number between 3 and 2. And if you multiply them together, you get 6. So that is the common number. To get my aluminum to 6, I need 2 of them. And that basically tells me I have 2 of these aluminums. +3 and +3 gives me +6. To get my oxide to 6, I need 3 of them. That tells me I have 1, 2, and 3 of them, -6. Everybody's balanced. And this would be the correct formula. This would be one where if you did do the switch down and across, you would be okay. You would actually get the right formula in this particular case. And lastly here we have sodium, which is a metal, nitride, which is a nonmetal, nitrogen. Sodium is group 1, which means it has a +1 charge. Nitrogen is group 5, which means it has a -3 charge. So when we put this together, we actually need more of the sodium. We need 3 of them to balance it out, and we should end up with Na3N. This means I have 1 nitride at -3, and I technically, if we drew them all out, have 3 sodium ions at a grand total of +3. +3 -3 gives me no charge when I put it together. Any questions on how to write the formula or to name it for type 1? So again, this is type 1, which is ionic compound, metals and nonmetals. Metals, the important part. Fixed charge, group 1, group 2, group 3. Silver, zinc, or cadmium. All right, then let's talk really about type 2 and sort of how we do that whole Roman numeral thing. And type 2, as I mentioned before, is essentially the same way that you name it, but the difference here is our metal is a transition metal. Our comes from below the staircase where lead, tin, those guys are hanging out. And they can have a variety of charges depending on who they're attached to. So if we take a look at what we got here on the page, which is FeCl2, when we look at this, we see iron, which is a metal, Cl, which is a nonmetal. So that tells us it's an ionic compound still. The iron is a transition metal, which tells us it's type 2. So that automatically should tell you I need to figure out what the charge is on that metal, because it could be something different. The good news is whenever you have a type 2 guy, you will always know what the charge is on the nonmetal or whatever it's hooked up to. In this case, we have Cl, which is group number 7, which means it has a charge of -1. The important part here is we don't have one of those guys, but we actually have 2 of those guys, which means grand total for our negative is -2. We know that an ionic compound needs to be balanced out to 0. And in this formula, there is only 1 iron present, which means in order to balance it out, it does need to be +2 in this case. So the way that we name that is still the same way as what we did with type 1. We would take the whole name of the metal, which is iron. We would do a Roman numeral of 2. And the 2 is the actual charge on one of the metals, the positive metal that you take out. It is not how many you have, which is a very common thing that people want to do that with. So the actual Roman numeral is if you took that metal out, that positively charged metal, what the positive charge is on one of them. The last part here named exactly like what we did with type 1, even though there's 2 of them, it is just going to get the IDE at the end of it, and this would be iron 2 chloride. And that is different, and you do need the Roman numeral because if you had something like FeCl3, this would again be iron that I'm not sure what the charge is. I do have Cl, which is Cl minus. In this case, I don't have 2, but I have 3 of them, which gives me a -3 charge, which means in this case, this iron is actually +3. So this guy here would be called, we'll go this way with it, iron Roman numeral 3 for the charge on it, and would still be called chloride. So the reason that we use the Roman numeral with type 2 guys, which are our transition metals, is because they can have multiple types of charges. We want to indicate to the person that's looking at it that in this particular case, we are talking about iron with a +2 charge versus the other case here where we're talking about iron with a +3 charge. So transition metals need to have Roman numerals, and including things just to the right there that I was talking about earlier, things like lead, tin, bismuth, antimony, that general region there on the periodic table will need some type of charge associated, or Roman numeral associated with it. Question on that one there. So right here, if we took this guy, take a second here and see what you would come up with the name on this guy. That's looking good. So let's talk about this one. I don't remember if it's on your notes or not. It might be, but just to make sure. When we look at this guy, what we want to look at is lead. Again, lead is not technically a transition metal, but it's one of those ones underneath the staircase on the periodic table that can have a variety of charges. So what that means is at this point, not really sure what the charge is on lead, but we do have the oxygen here, which is group 6, and that means it should have a -2 charge. We don't just have one of these guys, but we actually have 2 of them, which means if we add up all the negative charge going on over here, it is -4. And since there's only one lead, as it was correctly put there in the chat, we should have a +4 charge that it should be. And this guy would then be lead Roman numeral 4 for the charge on the lead. And again, even though there's 2 oxygens there, it is still just called oxide. I can tell you how often people will just go, this is lead 2 oxide because they did this move. Move the charge there, move the charge there. And this is a good example of that will not work correct for you in this case. As you can see there, you should actually get lead 4 versus lead 2 by switching it over. So it's really important to understand really what you're trying to do in terms of balancing the charges, because like I said, if you just sort of blindly do the switcheroo, 90% of the time you'll be okay, but you will run to a lot of situations where it will not work. So it's really important just to try to, you can even draw pictures like I do there, you know, with the charges and just add it up like that. So so the question is if we had PBO in that case, so PBO, we would do the same thing, and your first answer there would be correct. We would look at this case, and now we only have 1 oxygen present, which has a -2 charge. So to balance it out in this case, the lead would be 2, and it would be lead Roman numeral 2, and it would be oxide. Again, the reason we need the Roman numerals on these guys is because of just this. You have different charges that these guys could have, and you want to really tell the person pretty much this is the charge we're talking about in this situation. And that's really what all naming is really about. It's really just informing people, you know, this is sort of what we're talking about. The reason we don't need the Roman numerals on the other ones is because they have fixed charges, so they will always be those charges no matter what the situation is. So if you hook sodium up with whoever you want or however many of something else, it's always going to be +1 no matter the situation. And that's why we really don't need the Roman numeral. But in a case like we see here with lead, or previously what we saw with iron, it does depend on what it is hooked up with to sort of the charge that it has. And that's sort of the purpose of that. Other questions on that? Now, there's an older school way of naming, and we're not going to use it in this class, but in case you see it, sometimes they will use sort of the old version of the name or root of the name, if you will. So instead of something like iron, they will call it either ferric or ferrous. And the way that is usually named is the one with the IC has the higher positive charge. The one with the OUS has the lower positive charge. So sometimes that pops up somewhere like ferric, ferrous. Copper would be called cuprate or cuprous, cupric or cuprous, but we won't use that. So we'll strictly use Roman numerals in this particular case, and that's what you see here. That's sort of the, I won't say common name, but older way of sort of naming it. And you can see it's sort of a lot of the origins of the name of those elements. So we will definitely use this way, and you should use this way with the Roman numerals. And as you can see here, chromium with the +3 charge, chromium Roman numeral 3, chromium with a +2, Roman numeral 2. So again, you should definitely used a Roman numeral way, not kind of the older way of naming things. So as I mentioned before, and as we sort of talked about, the only real difference between type 1 and type 2 is in type 2, our metal is a transition metal, has a variety of charges it could have. So whole name of the metal, Roman numeral to indicate the charge on the metal, not how many, and IDE on the last guy, just like in type 1. So why don't you take a couple of minutes here and give the proper names for those, and I'll give you some names you can write the formulas for. So let's go with okay, guys on the left, give the proper name. Ones on the right, the proper formula. See what you come up with. Okay, so let's take a look here and see how we kind of get to everything here. So if we look at our first one, CO is cobalt. And if you find cobalt on the periodic table, it is a transition metal. So that automatically should sort of tell you I'm dealing with a type 2 compound, and also tells you that you need to figure out what the charge is on the cobalt. So because we don't really know what the charge is on the cobalt, that is why we want to look at the non-metal it's attached to. And whatever it's attached to, you will always know the charge. So Cl is group 7, which means it has a -1 charge because it's group 7. There again is not just one of those guys present. There is 3 of them, which means we have basically 3 of these guys. If we add up all 3 of these guys, it ends up with a -3 charge. And remember that whenever we put a metal and a non-metal together, the overall charge has to equal 0. So since we have all these non-metals adding up to -3, the only way to balance it out is that our cobalt here must have a charge of +3 to balance it out. And what that means is that this would be cobalt Roman numeral 3. And the 3 is not how many cobalts we have, but the actual charge on the cobalt. And even though we have 3 of these chlorides, we're just going to name it like normal, which is chloride. So this would be cobalt Roman numeral 3, because the cobalt has a +3 charge to balance out the negative charge, and chloride as the end there. Looking at this one, this is copper, which is also in the transition metal region. Again, should also tell you, I believe that we need to figure out the charge. So again, not sure what the charge is at this moment on the copper, but again, we do know that I is group 7 and has a -1 charge. So to balance out the -1 charge for the I, the copper here would have to have a +1 charge. Again, whole name of the metal, which would be copper. Because it could have a variety of charges, we do need to put the Roman numeral, which would be 1. And iodine becomes iodide, IDE at the end of it. Lastly, on this 3 here, we have SN, which is tin. Tin is not technically a transition metal, but if you look on the periodic table where that staircase is, tin is right about here, where I was talking about those guys that, although they are not transition metals, also have a variety of charges, and they're named the same way as transition metals. So if we look at this here, the tin, we're not sure what the charge is, but just like normal, we will know what the charge is on this guy, and that is group 7, and that means it has a -1 charge, and there's not one of them, but there are 4 of them. So if you just draw it out, that has a grand total of -4 for our negative, which means that our positive tin, because there's only one, would have to be +4. And this would be tin Roman numeral 4 for the charge. And even though there's more than one of them, not going to affect the name of our guy here. It is going to be tin 4 bromide. Question on any 3 of those names? Okay, so let's do the same thing over here with the writing the formula. The nice thing here, when we see copper Roman numeral 1, it does the work for us. That means that I have a copper, and the 1 here means it has a +1 charge. So we could use, obviously, our name to our advantage here. Nitride, IDE, tells us it's probably something from the periodic table. Nit sounds like nitrogen, which is group number 5, which means it has a -3 charge. So remember, when we put these 2 guys together, we need to equal 0. So in this case, we actually need more of the copper. So we actually need a grand total of 3 of those coppers to go with 1 of the nitrides. And that would give us Cu3N. And what that means is I have not 1 of those guys, but 3 of those guys. +1, +2, +3 balances out the -3 that's there for the nitride. Question on that one. Same thing here. If we look at the next one, chromium Roman numeral 3 tells me my chromium has a +3 charge, which is what that Roman numeral stands for. Oxide is oxygen, which has a -2 charge because it's group number 6 on the periodic table. When we put this together, common number there is actually 6. So to get my chromium to 6, I need 2 of them. 2 times 3 is +6. To get my oxygen to 6, I need 3 of them. 3 times -2 is -6. So +6 and -6, when I put them together, gives me no charge, which is equal to 0 in this case. And that would be the correct formula. And lastly here, we have iron 3. Again, iron is Fe. 3+ because of the Roman numeral. Phosphide is phosphorus on the periodic table, and that is group 5, I believe. So that is a -3. In this case, +3, -3. Just need 1 of each of those guys in this particular case, and we should be good. Any questions on any of those guys are type 3, or type 2 compounds. So type 2 compounds are essentially just like type 1, except you need that Roman numeral. Yeah, so real quick here, just grab something to kind of write on here. So on that one, we had chromium, which was +3, oxide, which is -2. So the common number here is 6. You could get that simply by multiplying the two numbers. So 3 times 2 is 6. So in order to get our chromium to get to a +6, I need 2 of them. Gives me a +6 overall charge. In order to get my oxygen to 6, I need 3 of them. Gives me a -6 charge. So +6 -6 gives me 0 overall charge. And at this point, you can just simply count what you got there. I got 1 and 2 chromiums, which is why I wrote Cr2. And here I have 1, 2, and 3 oxygens, which is why I wrote 3 oxygens like that. Again, the number goes to the guy to the left. So that tells me I have 2 chromiums, each at +3, +3, +6. The 3 goes to the guy to the left, tells me I have 3 oxides at -2 each, -2, -4, and -6. Gives me 0 overall charge when you put that together. Other questions or anything like that? Yeah, in a situation like that, if your question is to always multiply the charges, yeah, that will usually give you the simplest way to put it together. And whenever you put a positive guy and negative guy together, they should always come together in the simplest way to get to 0. There's multiple ways you could get these guys to 0. You could do like 4 chromiums and whatever, they're 9 oxygens or something like that, and that would equal 0. But it should always be the simplest way to put the positive guy and negative guy together that gets you to 0. So you always want the simplest way to do that. And when you multiply the charges together, that usually will give you the simplest whole number there that will get you to 0 when you put them together correctly. Other questions on that? You're welcome. Okay, we will stop there today. We're making some progress here. Good to see half of you or all of you for one day. We should do one day every week now, but twice a week next week. And for those that have discussion, I will see you in discussion. We'll start maybe at 7:05, get a chance to stand. I could use a standing break here, I think. And those that have lab, have a good weekend. And we're back to weekend again. And again, I apologize for the bad link. I'm not quite sure which one got copied in there. But the one for discussion I fixed just to make sure, so it should be correct. So go through that link that you see there in the module section. All right, if you're out for lab, have a good lab and a nice weekend. And for discussion, I'll see you in about 5 minutes or so. Make sure you pipe here if you didn't do so.